So in the last section, we talked about the Descartes signs, and when you reduced, the number is always by 2. And why is that the reason we always reduce by 2? And that's because if f of x is a polynomial with real coefficients, two things happen. If a plus bi is a root of the equation f of x is equal to 0, then you can also assume a minus bi is a root. The same is also true if I say that a plus b square root of c is a root when the polynomial is equal to 0, then also a minus bc is also a root. Now, this should make sense if we think back about what the quadratic equation says. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So what we have here is this plus or minus, right? And that is what guarantees us this idea of what's called a conjugate pair. Whenever one of these values exists, the other must exist. And that will always be true. So we're going to go ahead and start one of those questions. And we are going to be given, in this case, that 1 plus 2i is a root. All right, so what does this mean? Let's just take a second to review the vocabulary. All solutions to this equation, when this is a root, well, what does that mean? That means, where does this cross the x-axis? What we're going to do here first is combine the two conjugate pairs. So the first thing I need to do is I need to take the fact that I have 1 plus 2i. That is going to be one root. So I say x is equal to that. Now my second root will give me the fact that I know that 1 minus 2i is also a conjugate pair. What I have to do with both of these is multiply them together. Similar to if I have x is equal to 2, a root, and you bring that over, you get x minus 2. As part of one of the factors for this equation, I'm going to do the same thing here. And I'm going to make that x minus 1 minus 2i times x minus 1 plus 2i. Because again, what I'm doing with both of these is I'm moving them over to the other side of the equation so I can go ahead and use them as a factor. Now, the key to doing this easily is by grouping this piece here together and this piece here together, and seeing that this really and truly is just the difference of two squares when you go through and multiply them out. So when I do that, I have x minus 1 quantity squared minus 2i quantity squared. Multiplying all of that out leaves me with x squared minus 2x plus 1 minus 4i squared. I want to go ahead and replace that I squared with a negative 1, which goes ahead and leaves x squared minus 2x. This negative 1 turns that into a positive, and I get a positive 5. Now, this is a root that equals 0. It means what I have to do is take this and divide, and yes, you must use long division to go ahead and find the other two roots. So to go ahead and start long division, what we are asking ourselves is we are saying x squared times what will equal that 3x to the fourth, or mathematically it's 3x to the fourth divided by x squared, which is equal to x squared. So that's what goes up in the quotient. So now I go ahead and I take the x squared and multiply it times all three of those pieces and put it underneath, leaving me with a 3x to the fourth minus 6x to the third plus 15x squared. Now I need to go ahead and change the sign. That becomes negative. This one becomes positive, and this one becomes negative. I go ahead and add down. My first term cancels out by design. Then I'm left with negative 1x to the third plus 6x to the third. That gives me 5x to the third. Negative 7x squared plus negative 15x squared gives me a negative 22x squared. And now I repeat the process over again. I start with, all right, 5x to the third. What do I need to multiply x squared by to equal 5x to the third? So mathematically, that's just taking 5x to the third divided by x squared, and that leaves me with 5x. So that's what goes up in my quotient. Now I go ahead and take that 5x and multiply it times all three of the parts of my divider. And when I do that, I am left with 5x to the third minus 10x squared plus 25. Now, one of the things I need to do that I didn't do before is I have to bring down that next term, that positive 49x. And then before I can do anything else, I have to change the signs. The 5x to the third is negative, 10x squared is negative, and 25 also becomes negative. So when I go through and add all of that together, that cancels. I am left with negative 12x squared plus 24x. And I also now need to bring down that negative 60. And we are almost done with this. So last step, I ask myself, x squared times what will equal a negative 12x squared? And that answer is negative 12. I take that negative 12 and I multiply it times x squared. Two x squared and that positive 5. When I do that, I'm left with negative 12x squared plus 24 minus 60. And when I go through and change all of those signs, it becomes positive, negative, and positive, and all of that equals 0, which makes us all very happy. Because now we're done with that. And what does all of this mean? That means the function that we started out with, which was 3x to the fourth minus x to the third minus 7x squared plus 49x minus 60 is equal to x squared minus 2x plus 5 times what our quotient was, which was 3x squared plus 5x minus 12. Now, if you remember, this portion here came from our two imaginary solutions, so I know that can't be factored again. but I can factor the next portion. Our next portion can be factored out. Not sure why there's that little 2 hanging up. Let's get rid of that. So the next portion can be factored 3x for the first term and x for the second term. And we need this to be a 4 and a negative 3. So our final solution for this, meaning this first pair gave us 2 complex imaginary number solutions, and the next one will give us a solution that x is equal to 4/3 and x is equal to 3. So these would be our 2 solutions where the graph would cross the x-axis.